Alright, let's look at a special type of factoring. It's called the difference of squares. It's very popular and comes up more than the other special types. The other special type is called perfect square polynomials, and I did make a video for it, but it's not used all that often, but you should be able to factor those. But we'll look at difference of squares now, which everyone can do. The factors of difference of squares look like this: x minus 3, x plus 3. If you multiply that out, you actually get x squared plus 0x minus 9. And I'm purposely leaving a space for that 0x. Alright? We could look at x plus 2, x minus 2, and that'll be x squared minus 4. Again, I'm leaving a space for this 0x because it's kind of important. We could look at 4x plus 6 and 4x minus 6 will actually be 16x squared minus 36. And you can find out all these yourself by doing FOIL, or multiplying these two polynomials, or expanding, I guess would be the right way to look at it. So let's take a look at what we have here. There should be some obvious patterns that we're looking for between the product and its factors. Firstly, you'll notice that all of these products have both a positive factor and a negative factor. All of them. You'll also know I didn't write them all in the same order. It doesn't matter what order you write them in. If you multiply two values in either order, you will get the same result. That's the commutative property of multiplication. AB equals BA. So this times this is the same thing as saying this times this. So I could have written this in either order. Matter of fact, just because I can, I think I will. I'll change this, and I'll change that. So now I'll make that positive and this negative. Does it make a difference? Not at all. Let's look at the product and the factors for patterns. We have an x squared here, and both of our factors have x terms. Over here we have an x squared, and we have x terms. And over here we have 16x squared, and here we have 4x. So what's the pattern of consistency between these two things? The pattern is that the square root of x squared is equal to x. The square root of x squared is equal to x, and the square root of 16x squared is equal to 4x. Alright, if you're not sure why, 4x times 4x is 16x squared. Alright, so that's one pattern to notice. Another pattern to notice is that the square root of 9 happens to be 3. The square root of 4 happens to be 2. And the square root of 36 happens to be 6. Alright, so the general rule that we can see here is that given some square term, some number that has a square, minus another number that has a square, the difference of squares, their factors will be plus and minus, or the sum and the difference of their square roots. So the square root of a squared is a, and the square root of b squared is b. Alright, and that's true. So this is like our rule. Okay? So this is how you factor the difference of squares. Now we can compare that to trinomial factoring in these first two here. I did mention that it's sort of like having a, let's use orange, I never use orange, a 0x term here. I'm not going to do it for this because this is not a trinomial where a is 1, so this doesn't work the same way. The factors of negative 9 are plus and minus 3, so we have positive and negative 3. negative 3, and positive 3, and those add up to be 0. So that's why this works for another reason. The factors of negative 4 are negative 2 and positive 2. They add up to 0. There are other factors of negative 9. There's negative 9 and 1, and there's 9 and 1, negative 1, and neither of those add up to 0. So the difference of squares will be the square root because they have to cancel out or add up to 0. So they have to be the same, but the opposite signs. Same thing here. This also has 4 and negative 1. Does not add up to 0. And negative 4 and positive 1, which also doesn't add up to 0. So let's look at an example. If we wanted to factor, I don't know, 36 x to the 6th y to the 2nd minus 81 x to the 4th y to the 8th. We can see that this is a difference of squares because every term here has a square root. Now, if it doesn't have a square root, that doesn't mean you can't take the difference of square. You can't use the difference of squares. It just means you won't get a solid number when you do so. So, our factors, as we said, will be plus and minus, or minus and plus, doesn't matter. The square roots of the first term, and the square roots of the second term. The square root of 36 is 6. The square root of x to the 6th is x to the 3rd. And that's because x to the 3rd times x to the 3rd is x to the 6th. That's the definition of square root. The square root of y squared is y. So this gets the same value, because this times this will be this. Now the square root of 81 is 9. The square root of x to the 4th is x squared. And the square root of y to the 8th is y to the 4th. And as you might have noticed, when you normally FOIL two binomials, you'll actually get a trinomial. But in this case, there's a middle term that gets canceled out. Alright, so 6x to the 3rd times y times 6x to the 3rd y will be 36x to the 6th y to the 2nd. And then we multiply 6x to the 3rd y times 9x squared y to the 4th. You actually get negative 54 x to the 5th y to the 5th. And when we multiply this, we'll actually get positive 54 x to the 5th y to the 5th, which cancel out because they equal 0. And that's why they're not here. And then we'll multiply these and get negative 81 x to the 4th y to the 8th. Alright, so in the difference of squares, you don't need to use FOIL because the middle terms cancel out. Alright, so let's take a look at another example. Alright, let's erase that. And look at one more example. 5x to the 2nd minus 1. This is really not the difference of squares because 5 doesn't have a square root. So if you were to try and use the difference of squares here, we're going to get plus and minus the square root of each of the terms. The square root of 1 is 1. The square root of x squared is x. And the square root of 5 is actually the square root of 5. So this is really a stretch on trying to factor this. We wouldn't normally bother factoring something like this, but it can be done, because the square root of 5 times the square root of 5 is 5. X times x is x squared. 1 times 1 is negative 1. There would be the two canceling pairs as well. So this does work. Let's look at another example that does work. I don't know, pick a number, 16 x to the, just do 2nd, minus 9y to the second. So again, because this is a difference of squares, these are both square terms. They have a subtraction symbol. We get 4x, because that's the square root of 16x squared, plus or minus, plus n minus, I should say. The square root of this would be 3y. And again, it would also work if we wrote it in the opposite order. So if this was the minus and this is the plus, these would be equivalent, and you could check that by using FOIL, or just multiplying this out. And that brings us to a question that comes up a lot, and that is there a shortcut to factoring the sum of squares? So let's look at an example of the sum of squares, which some people ask about. Let's erase that. So the sum of squares, x squared plus 4. Can we factor this? And the answer turns out is no. This is unfactorable. And we'll look at why. The difference of squares has a rule, but the sum of squares has no rule. This is the same thing as this. So let's look at the factors of 4. We have 1 and 4, negative 1 and negative 4, and 2 and 2, and negative 2 and negative 2. And none of these add up to be the middle term, 0. So there is no two terms that would add up to be 0, so this is unfactorable. Therefore, the sum of squares is unfactorable. Alright? Because the factors of your third term, or your term here, will have to have the same sign. And because they have the same sign, there's no way for them to actually add up to 0, no matter what the example is. So the sum of squares is never factorable, but the difference of squares is always factorable. Alright, as long as the two terms are squares. The example before with the 5 is a real stretch. I wouldn't even do that one, ever.